Guys, my name is Ben, and I'm going to do a statically indeterminate problem.
Here's my setup. Basically, for this problem, I want to calculate the stress in each bar when the apparatus supports load W. My given values are to the side here. Let's see here. The diameter of cable is dA, so D is our center point here where the weight is loaded. So our cable DA has a diameter of 2 inches, as our cable DC does. Both these cables are aluminum cables. And then we have cable DB here and cable DE. Both those diameters are 1 inch, and both those are steel cables. So we have our given values for steel and aluminum at 30 times 10 to the 6 psi and 10 to the 6 psi. Our weight load is 15,000 kips, and then our two angles with respect to the y-axis are theta equals 30 degrees and alpha equals 45 degrees. Alpha is the cable DC with respect to y, and theta is the cable AD with respect to y. Now that we have our diagram set up, we want to find the lengths of our different cables using trig and yeah, just some trig relationships. So first we find our length of our DA cable, and that's just cosine 30, which is equal to adjacent over hypotenuse. So 20 feet is given to us along BD. So cosine 30 is equal to 20 over 80, which is our hypotenuse, and dA is equal to 23.1 feet. dB is given to us at 20 feet. DC is solved for the same way as dA, just we're working with our alpha. So it's cosine 45 equals 20 over BC. BC, I don't know why we have put BC. Let's see here. DC, there we go. Okay, so then DC is 28.3 feet, and then our DE was given to us right here as 10 feet in this cable. So those are our lengths. So now we have our different lengths. We have our length DA, DB, DC, and DE, or our cables. So we want to do the force balance for the x direction and the y direction. So for the x direction, we're going to have this component of this cable, this component of this cable, and our DE. I labeled our free body diagram as x, positive x in the right direction and positive y in the upward direction. So as you can see below, I did our force balance in our x direction. We have force of dA, which is negative, sine 30. We have force of DC, sine 45, plus force of DE, all equals 0. Okay, so our y direction did the same thing. So our force of dA, cosine 30, right, that's that component. We have a force of BD, because that's straight vertical, plus our force of DC, cosine 45, and then minus our weight, because that's straight downward. And you can see that there. Okay, so the second step in the statically indeterminate problem would be our force displacement. And basically what we're finding is we're seeing once we hang this weight on our apparatus, how much do these cables elongate or move. So this is, delta dA is how much our cable dA elongates. delta dB is how much our cable dB elongates, delta DC for DC, and DE for DE. So these are set up as force times length, force of the cable times the length of the cable, times its cross-sectional area, and modulus of elasticity. Excuse me. So cables DA and DC are set up as such because they're aluminum, so they have the cross-sectional area of the aluminum cable, and the modulus of elasticity of the aluminum cable. Cables DB, delta DB, and delta DE are set up this way because they're steel cables with the cross-sectional area of the steel cable and the modulus of elasticity for the steel cables. And like I mentioned earlier, that's just the force on each cable. Force on DB, force on DE, force on DC, force on DA. So those are the force displacements. Third step in a statically indeterminate problem is the compatibility. And so we want to relate the different deltas and the different stretching of cables to each other. So basically we're going to go back here to our diagram. And we see that when this weight is, sorry, let me get a pencil here. When this weight is attached to point D, it's going to stretch the whole apparatus downward. And so the amount that AD stretches in the y direction, the amount of the amount that CD stretches in the y direction is going to be the same value as the amount that BD stretches in the y direction. So I labeled my compatibility equations as such. Delta dA is equal to cosine 30 of delta dB, and delta DC is equal to cosine 45 of delta dB. Delta dB is our straight vertical cable. Delta dA is our cable running like this. And delta DC is our cable with respect to dB at 45 degrees running this way. At this point, it's really just plug and chug. So we have our relationships between our deltas, and we have our forces equations. So the first thing I did was solve for the area, cross-sectional area of the steel cables and the cross-sectional area of the aluminum cables. And in our problem, the diameter of our steel cable was given to us, and the diameter of our aluminum cable was given to us. So that was pretty straightforward. The cross-sectional area of the steel cable was pi over 4 inches squared, and the cross-sectional area of the aluminum cable was pi inches squared. And I just made one more note too, that that the diameter of the steel cables were equal to the diameter of the DB cable and the DE cable, because those two are steel cables, and same for the aluminum. Okay, so now I just plugged my deltas into my compatibility equation, and once again basically plugged in my numbers. I've solved for the lengths of the different cables. 23.1 feet for length of DA, 20 feet for length of DB. I know my cross-sectional areas. I know my modulus of elasticities for my steel and aluminum cables. And so basically I solved and saw that the force in DA is equal to the force in DB, which is pretty nice. I did the same thing, relating with our second compatibility equation, delta DC cosine 45 delta dB, to see that our force in DC is 0.666 force of dB. I have force of dA in terms of dB, and I have force of DC in terms of force of dB, excuse me. So I basically took those two forces in terms of dB, and I plugged them back into our summation of forces in the y direction. and solve for dB. So those are all our components of our y forces, and force of dB equals that value, which, if we can recall, is equal to our force in dA. So they both have that same value. I plugged that back into our relationship for FDC, which was right there, and found that FDC is equal to that value. Okay, so now I took our FDC and FDA, and I plugged it back into our summation of forces in the x direction, which, let me show you quick, was this equation right there. And let me find where I was at here. And I found, okay, so I could solve for f of d then, because I have f of dA and f of dc. F of dE equals 186.8.